All right, in Concept C, we're going to be learning all about how to analyze potential energy diagrams. So these are graphs that show what happens to potential energy as a reaction goes from start to finish. Now, the basic order of things. All reactions are going to start with reactants. So the potential energy always starts at the heat of reactants. So wherever our starting line is, that's the energy of our reactants. All right, all reactions, even those that release energy, exothermic reactions, require some energy to get started. This is known as activation energy. Okay, so I put a big star circle activation energy. That's a really important vocabulary term. So again, this is how much energy it takes to start. Now, potential energy diagrams represents the energy needed to have effective collisions between reactants particles. This raises the level of potential energy in the reaction to what we call the heat of activated complex. This is basically our intermediate step where everything's come together and collided. Our activated complex, again, intermediate step, reactions have to absorb the activation energy but have not yet actually reacted. The activated complex is very temporary and breaks down to form our products. This lowers the level of potential energy from that activation energy to the heat of our products. All right, so here we have a potential energy diagram. This is an exothermic reaction. I can tell that because here are my reactants, here are my products, and you can see that my energy of my products is less, so we're overall decreasing energy. Now, like I mentioned before, all reactions have to have a certain amount of energy to start. So this is like if you were riding your bike up a hill, okay, and you didn't make it all the way to the top of the hill, you would stay on that side and just go back to the reactants. Same thing with a reaction. If you can't get the right amount of energy to get you to the top of that hill, you're just going to stay reactants. You're not going to actually react. However, if you can reach the top, okay, and you can get enough energy to get up there, then you'll go over and make your products. Same thing with our reactants. If they can get that activation energy absorbed, they can then go and release energy as they form the products in this exothermic reaction. All right, you have this key on your note packet, but you need to set this up and fill this in. A is representing the energy of our reactants. So I would simply do whatever this number was minus 0, and that would give me my potential energy of my reactants. B is the potential energy of my products. This is where my products are. I would simply do that amount minus 0 and get the potential energy of my products. The heat of reaction, delta H, this is the difference between the energy of my products and reactants. So I would simply subtract products minus my reactants, which is represented by line segment C. And then finally, that very important activation energy, that's always going to be the difference between my reactants and the activated complex, which is up at the top. So I have A, B, C, and D that we just discussed. All right, you need to write this in on your note packet. Representing from my products going in the reverse direction is my activation energy of my reverse reaction. So it has to get up to the top, and then it reforms my original reactants. You also need to label the activated complex. Again, that's that intermediate step. Okay, that is basically a blend of my reactants and products in one big step. And this gives me, this line segment, the amount of energy that is in my activated complex. All right, now some things about potential energy diagrams. Many exothermic reactions are self-sustaining. Because they're continuously releasing energy, that provides the activation energy for other molecules to react. And also, if you haven't noticed, the forward and reverse reactions or equations of the same reaction are just mirror images of each other in terms of their energy diagrams. So that's why we could see that bike going in the reverse direction over that hill. All right, so here's an example of a forward endothermic reaction. Okay, here are my reactants. Overall, they're going to increase in energy, so my products are at a higher amount. Same thing as before. You have to make it up to the top, absorb enough potential energy in order to form those products. All right, so here again, you have this key in your note packet. You need to label everything. Okay, you have your line segment A, reactants. B is my products in this case. C is the difference between my products and my reactants. D is that amount of energy to get to the top of the potential energy curve. And then up at that top sits my activated complex. Okay, now this is one example of how these are set up. I'll talk tomorrow about when these line segments move around and help you use those to actually calculate amounts. All right, and then finally, if you can please label the activation energy of your reverse reaction. So if I went from products back down to my original reactants, because my forward reaction is endothermic, my reverse is exothermic, so keep that in mind. All right, so you are all set with potential energy diagrams in terms of your notes. We're going to spend 2 days working on this, so make sure you are all set and bring your notes with you to class to help support you.